Hey all, this is Mark with Omni Embedded, and this is Chapter F of the Vtrek Jumpstart Training Series. This chapter is about the real-time interface and data center blocks. So from the block diagram, this is the RTI. It rides on top of an abstraction layer that abstracts the RTOS, and here's the data center. We're not going to get too deep into theory in this part. That comes later in an advanced training series. But we do need to know a little bit about what an RTOS is and what it does. For some products, for simple products, you can get by with what's known as a super loop. And so this is a continuous loop that runs every n milliseconds, and every time through the loop, your processes are called, and they'll work and then sleep until the next interval comes. That's fine for some products, like a coffee maker, for example, is fairly simple. It doesn't have anything that's needs a quick response type of timing, and so a super loop would work fine for that. But most embedded products have control aspects that that you need the ability to control the response time on certain activities. And that's when you get into an operating system, a real-time operating system. These are preemptive priority-based multitasking schedulers. They're preemptive in that they'll interrupt a task that's currently running in order to run a higher priority task. They're priority-based, so you can assign priorities to tasks such that a higher priority task will preempt and interrupt a lower priority task. And the scheduler runs from a hardware tick source, which is usually a programmable interrupt timer, or in a lot of cases, the core of a microcontroller has a sysTick, which is basically there just for the purpose of running an operating system. So real-time operating systems are somewhat complex, and you really need to know how they work in order to avoid certain pitfalls that they have. Not just in general, but the specific product that you're running, the RTOS product that you're running, may have its own particular pitfalls that you need to be aware of. Some examples are shared resources. So if you have a shared resource like a SPI port, you may have 2 or 3 contexts that are using that SPI port, and each context is running from a different task, a different priority. And so you could have one context that attempts to use a SPI port that gets preempted by another task that then attempts to use a SPI port. And so you have to avoid those types of collisions. You have to manage that. You also need to write some of your methods as reentrant methods. You can have functions that are called and are partially through, but then get preempted and called again by a different context. And you need to make sure or get in the habit of writing functions that are reentrant. Priority inversion can be a problem, and this again has to do with shared resources, where a higher priority task is held off waiting for a lower priority task to release a shared resource. That causes jitter in the timing, and it causes at times whatever needs to run on that higher priority task to be held off too long. And then you can get into deadlock, which is where 2 tasks hold off each other while they're awaiting a resource that's held by the other. So a lower priority task uses a mutex to lock the SPI port, and then it gets preempted by a higher priority task that waits for the SPI port to be unlocked. And now you're deadlocked. Now, modern RTOS products have ways of working through and working around some of those pitfalls, but they're still prevalent, and you still have to be cognizant of the possibilities and be careful about how you use them. All right, so this little timeline kind of gives you an idea of how this works. We have 3 tasks, a 5, 10, and 20 millisecond tasks. The faster tasks are set to a higher priority. In an RTOS, priority 0 is the higher priority. And as we walk along here, we see that the 5 millisecond task runs, and then when the 10 millisecond task comes due, well, actually both of these are due because this is the second 5 millisecond interval. And since the 5 millisecond task has higher priority, it runs first, holds off the 10 millisecond task, and then when it's complete, the 10 millisecond task runs. And here's the same thing at 20 milliseconds. So this is the first time this guy's run, but the 10 millisecond and 5 millisecond tasks are also due. So the higher priority runs first, next highest second, and then the lowest priority runs last. And you can see that the lowest priority got held off for a period of time while the other two ran. Now this is normal. Here's another sequence that can happen. You've got the 5 millisecond task that runs, and then the 10 millisecond. And the 20 millisecond task runs long enough that the next 5 millisecond interval comes due. And so in that case, we're going to preempt the 20 millisecond task, let the 5 millisecond task run, and then the 20 millisecond task resumes and runs to completion. This is normal operation. This is how a scheduler works. And this slide gives us an idea of what's happening with the RTI. We'll look at the diagram first. This coincides with a previous diagram where we've got 3 tasks running. Each task is an infinite loop and has its own stack. And it will sleep, run, and it does this at a 5 millisecond rate. And every time it runs, what we do then when we transition to the RTI is we can attach what we call threads to the task. And every time the task runs, our thread functions are called, whatever we have attached to it. So these thread methods are not infinite loops. They're functions that are called and then returned. So that's known as a cooperative model, and there's a nice explanation of what a cooperative multitask model is at this wiki site. And so that's a transition between an RTOS and a cooperative task model. And this is how we're set up with the RTI. That makes things simpler. It really kind of hides the complexities of an RTOS and makes it much easier to use. So we're using the important aspect, and that's the scheduler. But many of the aspects that have those pitfalls are hidden away. So since we're using a cooperative model, we also need to be prepared to use state machines. In a cooperative model, since the function runs and returns, we may need to divide sequential operations up into steps. And that's where this utility, util_state_machine.h, comes in handy because it's a slick way of setting up state machines for this purpose. So the RTI can reduce or eliminate the possibility of those pitfalls that we talked about. And it can also make it easier to perform processing in the order that you need it to happen. And that's because we've added a feature to the RTI that you don't find in RTOS products, and that's a notion of having processing phases. So if we look at this diagram, and by the way, the package that we deliver has 3 phases already set up: an inputs phase, processing phase, and outputs phase. Now, these are configured in the RTI RTOS config.h file, and you can go there and add phases if you wish, rename them, reduce them, whatever you want to do. But the concept is to be able to make sure that things are processed in the order that you need them to be processed. So for example, if you have a process that needs to get a fresh sample of, let's say, an A to D channel, and then process it, and then the result of that processing becomes an output response, maybe a change in PWM or something along those lines. Then in order to make sure that you're working on the freshest data, you need to be able to know that that inputs like sampling A to Ds can be put on the inputs phase, processing can be put on the processing phase, and then driving the output to that PWM can be on an output phase. And again, you can add to these as you need. But this gives you a way of making sure that at any given moment, you're working on the freshest data that's been acquired from the outside. You can also use this to basically create sequences, if you wish, by creating more phases. So if you have two forms of processing that needs to be done, you could create a process phase 1 and a process phase 2, for example. So the defaults, as I said, are input, processing, and output phases. The way that they work are each task also has a group of phases based on what's in this configuration file. And when you attach a thread, you also specify, for example, if it's a periodic thread, you also specify which of these phases you want it attached to. So we've now added the ability to create a transactional model for data flow. Okay, let's switch gears from PowerPoint and look at some actual code that demonstrates this. The code module that I'm looking at is in Features under Product Logic, RTI Demo. And these two files were created from the ProDev tool, and then parts of it were implemented using the Snippets tool. The thread delegates were added with the Snippets tool, along with the functions that were needed for them. We have a periodic thread, a synchronized thread, an async thread, and a delay thread. And so to review, the periodic thread is going to run at the period of the task that it's attached to. The sync thread, the sync event thread, is triggered. It's an event, so it needs to be triggered. And once it's triggered, it will run from whichever task it's attached to. An async event is also triggered, and it's not tied to a task. It runs as soon as the thread that triggered it returns. And a delay thread is also not tied to a task. It runs after the specified delay is executed. And then we have counters, and then util stopwatch, or sys stopwatch, which is a stopwatch timer. We're going to use that to measure elapsed time. This is the elapsed time from when an event thread was triggered until it actually runs. So if we look over at the constructor, we can see how each of these threads were created, just calling a make periodic, make sync event, make async event, and make delay event method calls in order to create these. Periodic is tied to the 200 millisecond task on the processing phase. The sync event is tied to the 100 millisecond task and also on the processing phase. This choice is arbitrary in this case. The async is not tied to a thread, of course. The delay thread, the async is not tied to a task. The delay thread is also not tied to a task, but it is tied to a processing phase. And here we clear our counters. So in the periodic thread function, we have debug prints. So we're printing that we've entered the function. We're incrementing these counters. And then each of these counters has a different expiration count. So the sync thread, for example, it expires at 5. And at that point, we clear it. We print that we're going to trigger the sync thread, then we actually trigger the sync thread and mark T start. And the same thing happens for the async and delay counter. With the delay counter, we're delaying 720 milliseconds. So in each of these threads then, the thread method that's been attached, we're just using debug print to output the fact that we've ran this method, and this is the time that it took between trigger and method entry. So it's running on the K64 Freedom board right now, and I'm going to pull in the DDC tool and we'll have a look at what's happening. Now we're getting a lot of systrace messages, so I'm going to filter those by grabbing the name of the class, which we have in all the print statements, and using this as a filter. And then we'll clear, and let's see what we get here. All right, that's long enough. I'm going to pause this and we can go review and have a look at the data that we're getting. So here's periodic thread entering and exiting. In this case, it triggered the async thread. So that means that the async thread counter right here had hit 7, and so it reset and printed. And as soon as that thread returned, we got our async thread call, and it was 189 microseconds after we triggered it. On this occasion, we triggered the sync thread. And remember, we're running this at a 200 millisecond rate, so as soon as the 100 millisecond task ran, our sync thread ran as well. And so it ran at 100.233 milliseconds. And now we're doing some entering and exiting and entering and exiting, and now you see that the delay thread is run. That was actually triggered right here. So in this same pass, enter and exit, we triggered the sync thread and the delay thread both. And then the delay thread finally ran down here at 719.122 milliseconds. So you can see that the rates are fairly timely, and this pattern is just going to repeat at this point. But it makes it pretty clear as to what kind of flow we're getting and what kind of timing that we're getting out of this. So it demonstrates how these various types of threads are created or coded, created. It demonstrates how they run. Periodic, in this case, sync, async, and delay are all demonstrated in this. And so it should give you a good notion as to how these thread delegates are created and used in your feature code. So we have 3 best practices listed for RTI use. The first one is for periodic threads. And fairly often I see where implementers will tie a periodic thread to a much faster task than they really need to. And all this does is waste CPU throughput. Really, in your product requirement spec, there should be a response time defined for each feature, or for each input that needs a response. We really should have a response time defined, and there's really no reason to run any faster than the response time that's defined. So the rule of thumb is to run periodic threads as slow as you can get by with, and that's just to keep CPU overhead down. But more importantly, use event threads, because this is where a lot of CPU clocks and processing is saved. You can either run periodic threads and poll data, and it's entirely possible that you'll poll quite a few times before you actually need to respond. In some cases, with event threads, you only respond when you need to. So there's no monitoring, there's no polling. Just set your event threads up the way they're needed, and wait for things to happen. So this is really it's an event-driven paradigm that's meant to save CPU resources. And then don't forget about the util state machine.h. This is a slick way of setting up state machines or sequential processes that you may need when you're implementing threads. Okay, and the last thing on RTI or RTOS is I've put 3 links in here that are, I think, a pretty good read in terms of understanding how they work, the challenges that you'll face, and how to avoid those pitfalls.